Static scaling, configuring a fixed number of server instances, has a fundamental limitation. You provision for your peak load, but most of the time your traffic is well below peak. You're paying for capacity you're not using. Dynamic horizontal scaling solves this by adding instances when traffic increases and removing them when traffic decreases. But dynamic scaling introduces a new problem. How does your load balancer know about the instances that currently exist? If you add a new Node.js instance, your Nginx configuration file doesn't automatically update. This is the service discovery problem, and the solution is a service registry. A service registry is a database of currently running service instances. When a new Node.js instance starts, it registers itself with the registry. I'm available at IP address 10.0.1.5, port 3000. When an instance shuts down, it deregisters. The registry always reflects the current live state of your infrastructure. Consul, ect, and Zookeeper are the three most common service registries. Consul is particularly popular in cloud-native architectures because it combines service discovery with health checking. Consul regularly pings registered services, and if a service stops responding, Consul automatically removes it from the registry. No manual deregistration needed on crash. Your load balancer, whether Nginx or a custom proxy built with Node.js's HTTP proxy library, watches the registry for changes. When a new instance appears, it adds it to the pool. When an instance disappears, it removes it. The pool is always consistent with what's actually running. This is the infrastructure that makes autoscaling groups in AWS, Google Cloud, and Azure work. The cloud provider's orchestration layer manages instance count. The service registry ensures the routing layer always knows where to send traffic. The standard load balancing model puts all routing intelligence in a central component, the load balancer. Every request flows through it. This creates both a performance bottleneck and a single point of failure, even if you cluster the load balancer itself. Peer-to-peer load balancing turns this model inside out. Instead of a centralized balancer routing requests from clients to servers, each client maintains its own list of available servers and chooses which one to send each request to. There's no central routing layer at all. This sounds radical, but it's used in production by some of the highest traffic systems in the world. Netflix's client-side load balancing library, Ribbon, implements this model. gRPC's client-side load balancing uses a similar approach. When Service A needs to talk to Service B, Service A queries the service registry, gets the list of Service B instances, picks one using round-robin, least connections, or random and connects directly. The book demonstrates implementing this in Node.js, an HTTP client that maintains a list of server addresses, cycles through them for each request, and updates the list by polling a service registry. The core of it is surprisingly small, maybe 30 lines. The advantages are significant. No load balancer bottleneck in the hot path. No single point of failure. Routing intelligence can be more sophisticated because the client knows the context of its own requests. Failed servers are detected per client and removed from rotation independently. The disadvantages are real too. Every client must implement load balancing logic. Updating routing policy requires updating all clients. The registry must be highly available because every client depends on it. These trade-offs mean peer-to-peer load balancing is more common in internal service-to-service communication than for public-facing traffic. Before Kubernetes made sense as a topic, containers needed to be invented. And before containers, the problem they solved needs to be clear. The classic deployment problem: your Node.js application runs perfectly on your development machine. You install it on the server and it fails. Node.js version mismatch. A native module compiled for the wrong OS. A system library present on your machine but not on the server. Environment variables set differently. The infamous works on my machine problem. Virtual machines were the traditional solution. A VM includes a full operating system, which means the environment is fully reproducible. But VMs are heavy. Each one boots a complete OS kernel, requires gigabytes of disk space, takes minutes to start, and has significant memory overhead. Running 10 microservices as 10 VMs is impractical. Containers solve the same problem at much lower cost. A container is an isolated process with its own file system, its own process namespace, and its own network namespace, but it shares the host operating system's kernel. No duplicate kernel. No booting sequence. Containers start in milliseconds. A container image for a Node.js application is typically 50 to 200 megabytes. Docker is the tool that made containers accessible. A Docker file is a recipe for building a container image. Start from the official Node.js base image, copy your code in, run npm install, define the startup command. The resulting image contains your application and all its dependencies, frozen at the moment of build. Run it on any machine with Docker and you get exactly the same environment. Container images are immutable and versioned. Deploying a new version means running a new container, not modifying or running one. Rolling back means running the previous image. This immutability is a powerful property for reliable deployments. A container solves the environment reproducibility problem. But when you have dozens of microservices, each running multiple container instances, spread across dozens of machines, you need something to manage all of it. That's what Kubernetes does. Kubernetes is a container orchestration system. You describe the desired state of your system. I want 3 instances of the user service running, each with 512 megabytes of memory and 1 CPU core, and Kubernetes makes it happen and keeps it that way. If an instance crashes, Kubernetes starts a replacement. If a machine fails, Kubernetes reschedules the containers from that machine onto healthy machines. The core Kubernetes objects you interact with for a Node.js deployment are the deployment and the service. A deployment says how many instances of your container should run and with what resource limits. A service provides a stable DNS name and virtual IP address for reaching your deployment. Kubernetes handles routing traffic to whichever pods are currently healthy and running. Scaling in Kubernetes is a single command or a configuration change. kubectl scale deployment user service replicas equals 10. Kubernetes adds 7 more pod instances and begins routing traffic to them. The horizontal pod autoscaler can automate this based on CPU or custom metrics. For Node.js developers, the workflow is write code, build a Docker image, push it to a container registry, update the Kubernetes deployment to reference the new image. Kubernetes performs a rolling update, spins up new pods, waits for them to be healthy, then terminates old pods. Zero downtime, as long as your application handles the SIG term gracefully. This is the infrastructure layer that makes modern Node.js microservices practical at scale. Docker handles environment consistency. Kubernetes handles scheduling, scaling, and resilience. You focus on application code.